In this lecture, I'll discuss inverses of functions. I'll discuss their notation, how to take them graphically, and also how to find the inverse of a function using algebra. When we say the inverse, we also have to specify in math the operation. For example, if I had x plus 2 and I wanted to take the inverse of adding 2, it would be subtracting 2, and the result, I would get the x back. If I multiplied the x by a number and I wanted to take the inverse of that operation of multiplication, then I would use division and I would get the x back. When it comes to functions, they can be composed, even simple functions like a linear function. 5x plus 2, it contains both a multiplication and an addition. So there's no easy way to say how to take the inverse of a function. There's also, unfortunately, no straightforward way to denote the inverse of a function. Typically, if I wrote, say, 5 to the minus 2, that would mean 1 over 5 squared. Okay, if I have x to the minus 9, I can write that as a positive exponent by going 1 over x to the 9th. So the negative exponents do have mathematical meaning. You move from the numerator down to the denominator, or vice versa, the exponent changes sign. That's how it's typically done. This case is an exception. In this exception, we write f with a little minus 1 here, superscript here, right on the f. If we had g, we'd go g minus 1 and then put the x out here. And that would mean the inverse of the function f, or this is the inverse of the function g. Here's what you would think it would mean. You think it would mean 1 over f of x, following this pattern. But it doesn't. If you want 1 over f of x, then you have to write the minus 1 on the outside of everything. You'd have to put f of x in parentheses and put the minus 1 outside. This is very bad. This is a bad part of notation. Some astronomer actually decided to do this and felt like it would be okay. I don't know. I think it probably should have been rejected, and we should have had another notation for inverse, and we should have kept this idea that f to the minus 1 would be 1 over f, just like it is with variables and with numbers, but it isn't. So I have to point that out quite a bit because it's easy to forget it. So here I am pointing it out once more. F with the minus 1 as a superscript right on the f means the inverse of the function. If you want 1 over the function, then you have to put the minus 1 way on the outside after the x, after everything, of the entire specification of the function. Now, there are algebraic ways and there are graphical ways to take inverses, or to at least determine the inverse. For some functions, the only way you can find the inverse is graphically. So here I want to show you how it's done graphically. In this graph, here is the function f of x in red. The dotted line, that diagonal line, is y equals x. Now the graph of the inverse of the function is the reflection of f of x about that diagonal line. In other words, if you folded the paper along this diagonal line right here, then this blue graph, this blue line, would line up with the red line. Of course, it doesn't look so like it does. That's just because of the scale of this graph, but it does. So that's how you take a graph. You draw the graph of a function, the inverse of a function. You draw a diagonal line, and then you reflect the points from the function about that line over to the other side of the diagonal. How you do that with points is that if whatever you have on this graph, the xy, you invert the order and it becomes, can't even do it, yx on this graph. So what I had right here, that point is x of 0, y of 1. The corresponding point over here is x of 1, y of 0. So if you have a list of points, just reverse the order in the ordered pair and connect those points up, and there you'll have your inverse, the graph of the inverse. Now here's how to take the inverse, or determine the inverse graphically. You start off with some function. Let's just say it's 3x plus 6. Fine. Okay. Remember now that f of x was another name for y, so replace it with y. Okay. So this is the first step here. And in the first step, we replace f of x with y. And now you do, in the next step, algebraically what you did graphically in the previous step. You switch x and y. So I put the x here, and I've got 3y plus 6. So this step says switch x and y in the equation. And now, for the third step, solve for y. So I want y isolated, so I have minus 3y equals negative x plus 6. Dividing by minus 3, I've got y equals the third x minus 2. So here's your next step, solve for y. Okay? And now we need to show that it is the inverse. And to show that it's the inverse, we use composition. So if I have a function and I have the inverse function, when I compose them in any order, I could go f of inverse first, composed with f, then the answer is x. We get the x back. So like I said in the first slide, there's no real easy way to take the inverse of a function. So I'm going to use the functions I had before just to show you that the one I calculated worked. So I had 3x plus 6, and I worked through all those steps, and I came up with what I'm saying is the inverse function, which is 1/3 x minus 2. Now you can't just subtract these or multiply them and get the x back. Here's how you do it. You take f composed with f inverse. I'll leave off the x's just for clarity. F is the outside, f inverse is the inside. Here's the f. I'm going to put the 1/3 x minus 2 in here. Now I substitute that into the equation. 3, and now I will have 1/3 x minus 2. That x was not in the denominator. Whoops, I forgot to add 6. Distributing the 3 through, I get x minus 6 plus 6 equals x. Okay, let me show you another example. I'll do another linear equation, which f of x is minus 5x plus 12. First step, I replace f of x with y. Then I switch x and y. Alright, and now solve for y. So I'd have, 5y equals negative x plus 12. Divide through by 5, I've got y equals minus 1/5 x plus 12 over 5. And now to show that this is the inverse, I think I've got a sign problem. No, it's okay. Alright, and I'm calling this my inverse function here. So I'll do it the other way. I compose f of inverse with f. So f inverse is the outside, f is the inside function. Here's f inverse right here, and on the inside I put minus 5. This is a plus. That was my whole problem. Okay, so now let's work through that. I have a sign error. Okay, stop. I don't want to redo all this. So here's another linear example, just to learn the steps. F of x, say it equals minus 6x plus 24. First step, I replace f of x with y. Then I switch x and y. So the x goes here, and the y goes here. Now I have to isolate the y. So it gives me 6y equals negative x plus 24, dividing through by 6, I have y equals minus 1/6 x plus 4. And I'm saying that this is my inverse function. And now I check it by using composition. I can work the composition this way. So f inverse is the outside function, f is the inverse function. So that's f of, this would be minus 6x plus 24. Remember, I substituted for up here. Then I start evaluating this expression. Minus 1/6 times negative 6x plus 24 plus 4. I distribute through the minus 1/6 x and I get x minus 4 plus 4, and that equals x. I got the x back. This is the inverse. Here's a graph showing the first two equations. This is y, or f of x is 3x plus 6. Here is its inverse. This is f inverse of x being x over 3 minus 2. The dotted line, dotted green line is y equal x, the diagonal line. And these functions, it doesn't look so much like they're reflected about each other, about the diagonal line, but they are. For example, here we have the point x of 0, y of 6. Here's a corresponding point over here, x of 6, y of 0. Now, I've been saying repeatedly the inverse function. There is no guarantee that when you take the inverse of a function, you will get another function. If you add two functions together, if you subtract two functions, if you multiply them, you will again get a function. If you divide them, you get a function as long as you pay attention to the domains. But when it comes to taking the inverse, you don't necessarily get a function back. But there is a way to check to see if that inverse is going to be a function, and that has to do with the horizontal line test. Remember the vertical line test? So the vertical line test, to do the vertical line test, you would draw vertical lines, well, like that's a real vertical line, vertical lines on the function, and if you crossed it just one time, I'm looking at either one, the blue line, say, and if that vertical line hits the function at only one point, we'll even count that bad line, then if it only hits in one point, then then the equation can be called a function. Right, that's the vertical line test. The horizontal line test looks similar to that, but instead of drawing vertical lines, you draw horizontal lines, and you see if these horizontal lines will hit the function in only one point. In this case, it does. See? If that is the case, and that's your horizontal line test, if the function passes the horizontal line test, so if f passes, then the inverse is a function. And one reason for that is that when you take the inverse, when you reflect about the diagonal line, horizontal lines turn into vertical lines turn into horizontal lines. So if this doesn't work, then when it gets reflected about the x-axis, or I'm sorry, about the diagonal line, then over here you'll have a problem with vertical lines. And you can see that here. What I've drawn in red, this is my function, and it's just a parabola. It is indeed a function. It would pass the vertical line test, but it doesn't pass a horizontal line test. See, as I draw these horizontal lines, obviously I'm hitting the function in more than one point. So when I take the inverse, and I know the scale looks a little bit weird, but this is the inverse. When I draw that inverse by reflecting about the diagonal line, you see I now have a problem with vertical lines, so the inverse is not a function. I'll show you how that works algebraically. Let's say I have, well, the one I just did was x squared plus 4. This was my function f of x. I've already done the first step. I replaced f of x with y. Now I switch y and x. So I have x equals y squared plus 4, and I need to isolate the y. So I end up with y squared equals x minus 4, right? You can do that in your head probably. And now y still isn't isolated. I have to take the square root. But remember, when you take a square root, you end up with both a plus and a minus. The rule for a function is that for each x leads to only one y. But in this case, you could put a value of x in here. Say you put 29. So let's say x equals 29. Then you end up with plus or minus the square root of 25, which is plus or minus 5, so that when x is 29, y could be 5, or y would be 5, and also y would be minus 5. So this algebraically, you determine here that algebraically the inverse isn't a function, because for each x there was not just one y. In this case there were two.